and things that are sort of part of our discipline. And so as we go forward, we're now in Johnson Chapter 3, which I'm going to describe as the electrics of the situation. And so what we're going to do is, if we remember that everything in ECE is about informatics, then if everything in ECE is about informatics, and then the physical systems are technology dependent, then what we're going to be looking at today is going to be the electrics realization of the manipulation of information. So that's sort of a broad picture of where we are and where the context is. So what I'm going to try to do the best I can is to go back and look at the material in Chapter 2, but emphasize some of the elements of Chapters 1 and Chapters 2 as we go, and that way you'll start to see a better tie-in, I hope, than what Johnson does in the book. The other thing I want to point out is I'm going to not go in the same order as what Johnson does. Johnson's a little bit more traditional in his presentation, and I'm going to follow, I think, more of his intent than his actual way of doing things. I think that actually makes more sense. So I'm going to, for one thing, I'm going to ignore power and energy until I'm going to bring in the concept of impedance much faster than he does. And I'm also going to bring in something called the transfer function much faster than he does. So what you might want to do is take a look at the chapter as a whole and kind of get a sense of those topics and where they are. I'll try to make it easy for you in terms of finding what you need in the book, so you don't have to study every last thing all at once. You can go and read everything from a broad background, like you're reading a mystery story, and then you can dig in as you need to decipher what I'm up to. Okay, I don't see any hands up, so I'm going to go on. I'm going to start with something that you may have seen before, which is sort of the fundamental rule that we're going to be following. And this is V equals IR. And so this introduces three concepts. It introduces the voltage. And the voltage is actually very closely related to a force on an electron. So from a fundamental electromagnetics perspective, a voltage is very closely related to the force on the electron. So it's going to be providing the pull, or it's going to be providing the impetus behind any motion. And the motion that's going to happen is the flow of charges, and this is going to be the current, and this is going to be moving charge. So if you have things that have mass and have are moving, then you have a kinetic energy. And if you have a voltage, that's stored charge that's not moving but ready to move, ready to pull charge around, that's going to be potential energy. And we're going to tie those up together much better. But for now, we're going to be looking at voltage, which is stored charge, and current, which is moving charge. Stored charge, as we saw in one of our Wednesday lectures, has a lot to do with moving electrons around. And so what you're doing is the voltage will suck the electrons into a current, and it will move through a circuit. And what will deplete the voltage, what will deplete that, is something called a resistance. And that resistance is, in a pure resistor, that can be thought of as current that's electrons that are moving through an environment where a lot of collisions are happening. And those collisions are non-elastic, which means the energy is leaving electrics and moving into heat. And so if you're at home and you want a piece of toast, then what you're going to do is you're going to take out your toaster, you're going to put in a piece of bread. When you turn it on, the toaster is going to pull voltage from the wall, and it's going to current is going to flow through those heating elements. The heating elements are resistive. They're going to heat up, and that's why they're going to glow of that beautiful red, and that heat will toast your bread. So that's that in front of you is V equals IR, and so that's a nice electric heater. The units of voltage is volts. The units of current are amps, which is actually a coulomb per time, and resistance is ohms. And in the book, they talk about, and I'm not going to do a lot with this, but it's not a bad concept. They talk a lot about the conductance, which is 1 over the resistance, and the units of this are MHOS, which if you're awake this morning, you'll see is ohms spelled almost backwards. It's the OHM spelled backwards, MHO, which is as close to humor as us electrical engineers will ever get, I'm afraid. So this is a really a lot about what we need to be thinking about in this lecture and the next couple ones to follow is this V equals IR. But I'm going to generalize this concept of resistance right away. I'm going to say that this V equals IR works in a lot of it for other elements as well. And the meaning of R will change a little bit, but the fundamental Ohm's law, V equals IR, will stay the same. So the voltage will always equal a current flowing through a resistance, but in general, we're going to talk about Z, which is an impedance. And so that's going to be a generalized resistance that we're just going to tackle right off the bat. And the units of impedance will still be ohms. And it has to be because the resistance is going to be the ratio of the voltage over the current. So okay, so we're going to write R in terms of Z, and we're going to write Z in terms of V over I. Okay, so I want to talk about 3 fundamental components, and these are things that you buy and can hold in your hand. These are things that you can make in an integrated circuit, and they're actually more than just components. They're actually fundamental things that we can play with in electrics and even beyond, and even in electromagnetics. And so the 3 components are going to be a resistor, which has a symbol that is a squiggly line. And what that means is that's a tortuous path for the electrons to flow through. The device or the component is there to slow down the electrons, to provide a lot of not slow down so much as to provide a lot of collisions, and those collisions are going to lead to heat. So anything electric will leave the electrics and go into heat. So if you think about a conservation of energy, what you're getting is a loss of electrical energy and a rise of thermal energy. Okay, that's the role of a resistance. You also have a capacitor, and that's written like that, and we'll see why that's written like that. There's a reason behind that symbol. The capacitance stores charge. The capacitance stores charge, and so what these plates suggest is the possibility of charge building up on one and not the other. So it's hard for that charge to cross the boundary of that element. So it's a barrier, and we're going to see exactly what we mean by that barrier. The physical meaning of this is to store energy, and it stores energy in the location of charge. So if you take a balloon and you rub it with some fur, and then you hold it up to your hair and it attracts your hair, that's potential energy, that's charge forcing the charge on your hair to attract to it. So this has everything to do with potential energy. And you can see that potential energy is a very broad concept, which is why the capacitance is also a very broad element. And if you remember again from that Wednesday lecture on how to read an equation, we had an electromagnetic equation, the force equation, and there was an epsilon naught in it. And epsilon naught had the same, almost the same units as a capacitor. It had units of farads, and epsilon naught had units of farads per meter. And so there was an acknowledgement in that law, in that electromagnetics law, that potential energy was an important piece of the puzzle. And so in a circuit level, the role of potential energy is played by the capacitor. And the last element is L. And in a few lectures, when I have more confidence with Zoom, I might actually call on somebody to tell us the role of what the inductance is. I'm feeling a little bit shy on our very first outing, so I'm not going to do that. This L is called an inductor. And if the capacitor talks about potential energy, then this will talk about kinetic energy. That'll talk about kinetic energy. And so the interplay between the inductor and the capacitor, the mu naught and the epsilon naught, is an interplay between kinetic energy and potential energy. And the interplay between kinetic energy and potential energy is always going to lead to a sinusoid, or perhaps with a resistor to a sinusoid that's losing its amplitude exponentially. So if you think about a pendulum going back and forth, you're going to have, when the pendulum is high, you have a lot of kinetic potential energy. As it falls, it moves from, that potential energy gets moved into kinetic energy. At the very bottom, it has no potential energy, all kinetic energy. The movement goes up all the way and transfers again into kinetic energy. So the movement back and forth will give rise to a sinusoid in time, and it will come from exactly that trade-off between potential energy to kinetic energy to potential energy to kinetic energy. If there's air friction, or we're doing this in a fluid, there's going to be damping, and that pendulum will eventually stop and die down. The amplitude of the oscillations will die down, and that's modeled as a resistive loss. Okay, I said that we were gonna generalize on the resistance. And so the next step to do is to find out how we generalize on the resistance for the capacitor and for the inductor. So what is the impedance, and this is generalized resistance of a capacitor? And the way to do this is to start with the fundamental equation that describes what the capacitance is in terms of the current and the voltage. And I'm not sure if everybody has seen this equation. But it is the current is equal to the capacitance multiplied by the rate of change of the voltage. So if the voltage has a rate of change, if it's a signal that has a derivative on it, then the current that flows is the slope of that signal. It's the rate of change of that signal. So the current is related to a derivative of a voltage, not the voltage that we saw in the resistance. So there's a bit of a difference here. Okay, so what might we do? And I think one of the ways we'll do this is we will. Trying to pick my favorite blue here. One of the things we'll do is we will use our favorite signal. And so we're going to write our favorite signal as a sinusoid. And I'm going to write it in complex notation. I'm going to use e to the j omega t. So I'm going to assume that there's one frequency component. I want to just know what happens when a sinusoid goes through this equation. But I also want to point out that I'm being very general about what omega is. So Rachel can be thinking of an omega that's 10 kilohertz, and Matthew can be thinking about a signal that's 10 megahertz. And so in both cases, this will happen. And then Ziyu is also thinking about this, but in her system, it's music, and so she has a variety of frequencies that are all at play. Okay, and so we're considering one of those notes on Ziyu's piano that she's thinking about in her problem. And so if I take the derivative, well, okay, so if I take the derivative of this. The exponent is one of the easiest things to take the derivative of. Because what I get is I get exactly the same exponent, e to the j omega t, and and then multiplied by what the argument in the exponent is, the j omega. So I have dv dt is equal to the amplitude of the voltage times j omega. The omega is the frequency that we're interested in, or in Ziyu's case, all the frequencies. And we're going to see a little bit later what j means. So just let that kind of stew and mystify us for a little bit. Now, if the derivative of the voltage if the time dependence of the derivative of the voltage is still e to the j omega t, this is the full time dependence of the voltage. This is also then the full time dependence of the current. So I have I is equal to I naught e to the j omega t. And so I have the equation I naught e to the j omega t. That's this piece here, is equal to C. That's this piece here, times V naught j omega e to the j omega t. And the first thing you know is that we have an e to the j omega t on the left-hand side, we have an e to the j omega t on the right-hand side. The time dependence cancels. So there's now no time dependence in this equation. There's now no time dependence left in our equation. If some of you may have already looked at a little bit of differential equations, or maybe even a lot of differential equations, and in the parlance of that course, we have just solved this differential equation because we've guessed a correct solution to that differential equation, and the time dependence has dropped out, and so now what we're left with is the interplay between the parameter omega and then some constant, then the amplitudes and a constant or two. So now what I'm going to do is I'm going to go back to this equation here, and I'm going to say, well, wait a minute, I have a V over here and I have an I over here. What is my V over I? So V over I, so I divide through by the I naught, and then I divide through by the C, I divide through by the J, I divide through by the omega. So I get V on top of I naught is equal to 1 over J omega C, and this will equal to the impedance of the capacitor. Okay? So this plays the role of the resistance or the impedance of the capacitor, and very, very naturally, it's frequency dependent. So Rachel's 10 kilohertz component is going to have a different impedance than Matthew's 10 megahertz component. Matthew's 10 megahertz component is going to be 1,000 times lower in impedance or resistance, generalized resistance, than what Rachel has to suffer for the same capacitance. Or perhaps if Matthew and Rachel want the same generalized resistance in their circuits, they're going to use different values of capacitance to achieve that. And so that's the meaning of having a capacitance impedance, which is a function of the frequency, omega. Okay? So we have a resistance. V equals IR for the resistance. we have a capacitance, V equals I over J omega C for Ohm's law for the capacitor. And now what we want to do is, what is it for the inductance? And I forgot to tell you this, that the units of the inductance are henries. So what I want to do for the inductor is find exactly the same law or the corresponding rule from electromagnetics for the inductance. And these came from a variety of experiments that were done in the 1800s, where scientists were around the world were trying to ferret out what the interactions were between paraffin wax and lemons and electrons and all these, and keys hanging from kite strings and all this stuff. These V equals IR, this I equals C dV dt, and then this last one, this next one, V equals L di dt. That's all a consequence of those experiments. And so again, what we're going to do is we're going to assume that V is equal to V naught e to the j omega t. We're just going to interrogate this inductor with one of our favorite frequencies. It follows that if the voltage is sinusoidal, then the current will also be sinusoidal. And if I substitute this in, so this equation here into the voltage gives you this. The right-hand side has an L in it, and then the derivative of this, and I'll do this out on the side here. I have to take the derivative of the exponent, and the derivative of the exponent gives me back the exponent with this element coming down. And so I'll have an I naught, a j omega, and an e to the j omega t there. And again, because of the niceness of this equation, and a lucky guess, or a reason why we have a favorite function like a sinusoid, the time dependence cancels. The time dependent cancels. And so I can write an equation for V naught over I naught. So I just divide through by the I naught, and I get L j omega, which is equal to Z, the impedance of the inductor, and that's equal to an impedance that's still a function of frequency. But it's really beautiful that the capacitance the impedance of the capacitance is 1 over j omega. The impedance of the inductor is j omega. So j omega is in both of those, but in one it's in the denominator, in other it's in the numerator. And so if I just plot those, for the capacitor, actually, let me go back to here and plot it. I have a curve that looks like that. Notice what happens at 0. Omega equals 0 is infinity. That has major consequences. If I plot this inductance for if I plot the inductance impedance, then my impedance is 0 at 0 frequency or DC, and then I just have a nice straight line going up. So just fun with functions. I've got a function that's a function of omega. I've got something that's a function of omega. One is 1 over j omega. One is proportional j omega. And I've just reminded you of what those curves look like. Okay. And I'm going to draw that a little bit nicer. Notice that at very, very, very large frequencies, the capacitance goes very, 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 very low. So let's take a look at limits. We'll look at the pictures in a different way. And I want to look at two limits. I want to look at omega equal to 0, and that's the DC case. That's a battery. And then I also want to look at omega equals infinity, and this is a very high frequency. Okay? So at DC, I have Z capacitor omega equals 0 is equal to 1 over J times 0 times C, and that equals to infinity. And what that looks like in a circuit is a wire that stops. There's a big gap, and then the wire continues again. And there's no way that the electrons can jump across this gap. So that's an open circuit. That's an open circuit. And then the other case, at infinity, one over infinity is 0. And here's what that looks like. That's a short circuit. At very high frequencies, the electrons just cruise right across that. So if you're looking at a circuit with a tangle of capacitors in it, you could redraw your circuit in these two limits and very, very quickly get an intuition about what the circuit is trying to do. How does it behave at DC? How does it behave at very high frequencies? Then you're really just left with a bunch of open circuits and a bunch of short circuits. And things can happen pretty fast. So I'm going to do an example of that. And then we'll stop for the day and take care of a couple of things and so on from you guys. example, and I want to just consider this signal. And this is some voltage as a function of time. And it has a DC part of it. And it has an AC part of it. And if I plot this, I'm going to have a sinusoid. This is V as a function of time. Have a sinusoid where this value is VDC, and this value here is VAC. And then I want to send this guy through So I'm going to have VDC plus the AC part of it, the alternating current part of it. Notice how I stuck in a term of art there, direct current and alternating current, DC and AC. That's a pretty common vocabulary term for electrical engineers. You may have heard about it. If you haven't, then this is what we mean by it. We did a homework problem with 60 hertz, and that was the AC component on it. Okay, so for the DC case, this goes to an open circuit, and if this is the input, and this is the output, nothing gets through because the capacitor blocks DC. And then, just in the limiting case, I'm going to say that the alternating current is very, very, very high. So this will go to a short circuit, or if you want to be really precise, a resistor with a value of 1 over J omega AC times C. And the output will be that coming through in the short, if you're doing a short circuit analysis, or if you're being more careful, it's going to have a voltage that's a little bit lower than what's going through. And I'm not going to, I don't want to go through completely what that means. But if I have to sketch the output, V as a function of time, then this piece here, this component here goes away, and all I'm left with is a signal that oscillates around the axis. Okay, next time we'll review this a little bit. Okay, actually, let me amend that. Next Monday, we'll get back into this. We'll review this and we'll do inductors and we'll do some circuits to analyze that. On Wednesday, I'm going to go over the homework that's due today. Remember, that's from chapter 2, so that'll serve as a review. I'll pause now because I see a couple of you have unmuted. Do you have any questions?
Yes, I was wondering if you could go back to the slide right before this. Thank you. And I'm just a little bit confused on like, why did this signal move down?
Ah, okay. So let's okay. So I'm talking about a signal, and the signal I've constructed has a DC offset, a CW. This is not a function of time. And then I have an AC part of it, which is a cosine as a function of time. Mm-hmm. And so if I plot that, I get a VAC that's riding on top of a DC background. So Lauren, do you see this graph here?
Yes.
Good. So now what I'm going to do is I haven't said it, but I'll say it now. I'm going to use the principle of superposition. And I'm going to look at separately what happens to this frequency component and this frequency component as they meet a capacitor. Mm-hmm. And because I have an infinite impedance, at omega equals 0, what was that, Lauren?
Sorry, that was just the phone.
Okay, so I have an open circuit here, so nothing gets through, so the output is 0. And so this piece of it on the output goes away, and the sinusoid falls down to 0.
Okay, that makes more sense. Thank you.
Other questions? This hasn't been as interactive as I like it. I apologize for that.